All right, so today we're going to be talking about the concept of quantum entanglement, the EPR paradox, and violation of Bell's inequalities. So we'll start off talking a bit about what entanglement is, and then sort of go into what Einstein thought of it and his problems with it, and the paper he published with his colleagues Podolsky and Rosen in the early 1900s. And then we'll talk about what a Bell's inequality is and the experiments that have been done that show that you can actually violate Bell's inequalities. So there's this nice quote here by Einstein, which is kind of fitting. It's essentially him complaining about certain features of quantum mechanics, which, it's not an unreasonable complaint to make, I'd say, at least at first glance. There's a lot of things about it that seem unintuitive. And here he famously is talking about spooky actions at a distance, which is something we're going to talk about here soon enough. So, oops. So first we can start off by talking about what exactly is quantum entanglement. So strictly speaking, in a formal mathematical sort of sense, an entangled state is a state that you can't represent as a direct product. So a direct product representation looks like this here in the middle of the screen. So you can imagine if we had a composite system consisting of several subsystems, say subsystems 1 through n. If you can represent the entire state of the system, so this ket vector here, if you can represent this as a product of the individual subsystems like this, that's a direct product representation, okay? So if you have a state that can't be represented in this form, we call that state entangled, okay? So a very common example of an entangled state that every physics student will see in their career is a singlet state for two spin 1/2 particles. So that's shown down here. As you can see, we have a sum of two states here. It's not written as simply a product. No matter what we do to this state, we're not going to be able to rearrange it so that we have a product of kets. We have a ket here, we have a plus C minus C ket, and then we have a minus C plus C ket, right? And they're written here as a difference or a sum between the two. So that's a common example of an entangled state, and that's what it is in a mathematical sense, but we're physicists, so let's go on to look at a physical example. So the most common example explaining quantum entanglement that you'll find it in pretty much every standard physics textbook. It's everywhere. Is the situation is as follows: we have a spin 0 particle initially at the origin, okay, at t equals 0, and let's say it's at rest. And then sometime later, the spin 0 particle decays into two spin 1/2 particles. Now, due to momentum conservation, the two particles are going to have to go out in opposite directions, right? And to conserve angular momentum, we know that one of the spin 1/2 particles will have spin z going up, and the other one will have spin z going down, all right? Now, according to quantum mechanics, we don't know which is which, but we know one of them has to be up and the other has to be down when we measure them. Okay, so you can imagine particle 1 going over here to the left towards a Stern-Gerlach z direction detector. So we'll say Alice has control of that detector. And then we have Bob over here for the second detector to measure particle 2. All right. So let's talk about what happens when we make a measurement on these particles. So if Alice measures SZ, there's a 50-50 chance, assuming the particle is in this singlet state, 0-0 state, which it does have to be since the total spin we started off with spin 0. So Pauli exclusion principle says we have to have the anti-symmetric state, which is what we have here. So if Alice measures SZ, then there's a 50-50 chance she's going to get spin up or spin down along Z, right? So suppose Alice measures particle 1 and she gets plus Z as her measurement. If that's the case, then we immediately know after that measurement is made that Bob has to measure particle 2 to be down. If Alice is up, Bob must be down. So if we only know what Bob's spin component is, if we only know that Bob measures particle 2 to be down only after we measure A is up, does that mean that somehow the measurement made by Alice is somehow affecting the measurement made by Bob, right? Because it's right after we measure particle 1, right after Alice measures it, that we realize that Bob has to be the opposite. So is there anything strange about that? And at first glance, it doesn't necessarily have to be the case that somehow detector A is influencing detector B. I mean, you can explain this completely classically because you could say, well, if Alice measures spin up and Bob measures spin down, well, maybe from the moment that decay of the spin 0 particle first started, maybe they started off in that state initially, and then they just went their separate ways, and we measured them, and that's what we found. So it would be akin to if you had 2 balls in an urn, for example. If I had a black ball and a white ball, I reach my hand in the urn without looking, and I pull out one of the balls. And if I open my hand and I realize it's the black ball, well, then I would say, even before opening my hand to figure out what ball I'd grabbed, I'd say that in my hand all along I had the black ball, and all along the white ball in the urn was white. So there's nothing too strange about that initially. We can explain all the results we've seen so far with classical mechanics. So, but we know from experience that this typical problem of 2 spin 1/2 particle decay, or sorry, spin 0 particle decaying in 2 spin 1/2 particles, it's a classic problem that shows up, or a classic experiment that's shown in every quantum mechanics textbook. So if it's in a quantum mechanics textbook, it probably can't be explained with classical mechanics, right? So what about this is strange? So the strangeness of this comes into play when we consider both measurements along the z component of the spin, or along the z-axis and along the x-axis, okay? So Sakurai, in his textbook, he has a nice table here of all the different possible combinations and results that you could get. So Alice can measure along X or Z, and Bob can measure along X or Z, and they can measure along the same axis, they can measure along different axes, whatever the case may be. All right. Now, if you take the time to look at this table a little bit, what you'll figure out is that if Alice measures along Z and Bob measures along X, then there's random correlation between the measurements. So for example, if Alice measures spin up along Z, Bob's going to measure 50-50 probability, SX is going to be up along X or down along X. There isn't any correlation between the measurements at all. It's completely random. So, but now if you look at the situation where they're both measuring along the same axis, so suppose Alice and Bob are both measuring along SX. Now it's the case that you observe is that they'll have opposite signs, right? Very similar to when we were just measuring along SC, right? We found that they always had opposite signs. That was the experimental result. Same thing here. If both are measuring along SX, they're going to have opposite signs. So one will measure spin up along X, the other will measure spin down along X. So what you can conclude from this is that So B is measuring along x in both cases, but depending on which case we consider, A can be measuring along z or A can be measuring along x. And depending on what Alice chooses to measure, it affects the outcome of what B measures. Okay, so at least according to a quantum mechanical theory, it seems that what Alice does at her measuring device, what she chooses to measure, somehow affects the results of the measurements made at B. And it doesn't matter how far away the measuring devices are from each other, you could have them, one of them be on Earth and one of them be orbiting out past Neptune. You would still see this sort of effect. Okay, and this idea was something that Einstein wasn't too thrilled about. So he said, quote, "But on one supposition, we should, in my opinion, absolutely hold fast. The real factual situation of the system S2 is independent of what is done to S1, which is spatially separated from the former." So Einstein was very well known for um, not taking too kindly to the idea of quantum mechanics. He didn't like the idea that things were probabilistic. He didn't like the idea that somehow there wasn't a definite momentum and position of a particle that we could know at the same time. So quantum mechanics in general for him wasn't something that was it wasn't something he was necessarily too happy about. But he's, out of all of the unintuitive, strange things that came out of quantum mechanics, he said if any one of these things had to be wrong, it's this idea that somehow I could have two detectors that are light years away from each other, and the measurements I make over here at detector A can somehow influence the measurements that are seen at detector B, even when they're extremely far away from each other. So this idea was something to him that he couldn't reconcile with any reasonable view of reality. So his workaround to sort of get around quantum mechanics was that his interpretation was, well, imagine a situation where we're measuring along z, and we're measuring along z on many particles which are in the state plus x, right? Now, quantum mechanics says that 50-50 come back plus z and minus z. We can write the state down for that, describes that, right? We write plus x in the basis of z and see that written out explicitly. So Einstein could perfectly well believe that maybe if we measure 50% of the particles being up and 50% of them being down, maybe just 50% of the plus x particles were up and down along z to begin with. Maybe from the moment they started going towards the detectors, that was already the state they were in. And it's just that quantum mechanics wasn't able to tell us that they were in that state all along. Okay? So this idea still keeps with the experimental results, but it just circumvents the need for quantum mechanics. So this type of theory is known as a hidden variable theory, the idea being that there is some piece of information or there is some variable that quantum mechanics is missing or quantum mechanics can't tell us about, which would allow us to distinguish between the particles being spin up or down along Z. Okay, so this idea was introduced in a paper, the EPR paper, with his colleagues Podolsky and Rosen, and for the time being, after this was published in the decades to follow, it was perceived as a viable option that was just as viable as quantum mechanics. Nobody immediately saw anything wrong with it. So this was Einstein's take on the whole situation. So an example of a hidden variable theory that will perhaps make it a bit more clear is, so we can imagine four distinct groups of particles for particles 1 and 2. So we can imagine particle 1 having plus z and plus x angular momentum. and you can imagine particle 2 having minus e and minus x, and then there's 3 other possible arrangements that we can have. So these braces here are used to represent the actual components of spin that the particles have, okay? So if we assume that all of these 4 different groups, imagine following a spin 0 decay, all of these 4 groups are produced in equal numbers, okay? So if that's the case, if each of these groups is produced in equal numbers, well, then you're going to get the same experimental results that we already saw. So you can get the same experimental results here, but without needing to invoke any sort of quantum mechanics. So it seemed as if this could be, a possible alternative. It seemed to fit the results that we saw still. So is there a problem with this? Could this be an alternative to quantum mechanics? And the answer was for a long time that people thought it could be, but in 1964, um, John Bell figured out a reason why it perhaps couldn't be, or more specifically, he figured out a testable inequality, a way that we could do an experiment to test and see if a hidden variable theory was correct or a quantum mechanical theory was correct. So there are some differences between the two theories that actually matter and translate into different results experimentally. Okay, so an example of a Bell inequality is if we consider 3 coplanar non-orthogonal directions. So we have unit vectors a hat, b hat, and c hat that we can measure spin along, all right? And in that particular configuration, there's 8 groups there's 8 different groups that particles 1 and 2 can be in, and they're listed here down below. So populations 1 through 8. Notice that if whatever the sign is on a particular component for particle 1, that sign is going to be opposite for particle 2. So we have, for example, in population 3, we have plus A, minus A, we have a minus B over here, so we have a plus B, we have a plus C, so we have a minus C over here, right? So out of these 8 different populations, if we imagine that Alice and Bob choose to measure the spin of the particle along different axes, okay? So if Alice and Bob choose to measure along different axes, you can show that for populations N2 through N7, that A and B are going to yield results which have opposite signs 1/3 of the time, okay? And for populations N1 and N8, if you look at those, you'll notice N1, just wait for that to go away. Well, if we look at N8, for example, you'll see that particle 1 is all negative, particle 2 is all positive, and the inverse is true for N1. So in those cases, anytime you measure a particle belonging to N1 or N8, you're always going to get opposite signs, right? So that means for a given pair of particles, particle 1 and particle 2, if A and B measure along different axes, at least 1/3 of the time we should expect that particle 1 and particle 2 come back having opposite signs, okay? So this is an example of a hidden variable theory, and this result of having at least 1/3 of the measurements come back being opposite signs, this is an example of a Bell inequality, okay? So, but as we'll see, this Bell inequality from hidden variable theory, it's in contradiction with quantum mechanics. So if we do a more specific example here where we imagine the axes A, B, and C are all at 120 degrees to each other. So you notice this picture up here, it kind of looks as if A, B, and C are perpendicular to each other. When I first look at this, it sort of reminds me of X hat, Y hat, and Z hat being perpendicular. They're not in this case, so these are all in the same plane, just separated by 120 degrees from each other. So in this particular situation, you can show that if Alice and Bob are measuring along different axes, so for example, if Alice is measuring along A and Bob is measuring along B, you can show that the probability that they get opposite signs is 1/4. All right, and it's 1/4 for any situation in which Alice and Bob are measuring along different axes. So Alice measures along A, Bob along B, Alice along A, Bob along C, etc. It always comes back a fourth. Now this result is is a result from quantum mechanics. So quantum mechanics is telling us that I should see opposite signs 1/4 of the time, versus a hidden variable theory over here is saying I should see opposite signs at least a third of the time. So if we do this experiment, one of these theories is going to come back correct, and one of them is going to be wrong. All right. So that was just one example of a Bell inequality. Bell's inequalities in general, it's a more general term that refers to any sort of inequality that you can use to experimentally distinguish between a quantum mechanical theory or a hidden variable theory. So there's another example here off to the right-hand side of the page, just to show that you can come up with other inequalities to test. All right. So the basic idea is if you have a Bell's inequality and it's violated, then a hidden variable theory is incorrect, and quantum mechanics is still the best theory that we have to explain the results that are going on, right? Now, so far, and again, in every textbook, the most common example you see is to spin 1/2 particles. There is only one experiment I know of that has actually used to spin 1/2 particles. It was done with protons to test a Bell inequality, but almost all of them in practice, instead, what we're using is photons, so pairs of entangled photons. And rather than measuring spin, we're measuring polarization along a certain axis, right? So you can sort of imagine it's not too big of a leap. You can imagine an analogy between, well, instead of measuring spin along a certain axis, now I'm just measuring polarization along a certain axis. So you can develop the same sorts of inequalities there. So a very famous, well-known experiment was done by John Clauser in 1972, along with Stuart Friedman, to test a Bell inequality. So the situation there, which is depicted down at the bottom of the screen, is so you had a calcium atom, and if you shined a particular type of light on the calcium atom, what it would do is it would emit entangled photons. And just like with the spins, once we had particles that were emitted, we can now, instead of Stern-Gerlach detectors, we can have polarizers. Okay, so we can have a polarizer along axis 1, and we can have a polarizer along axis 2, and we can do the exact same sort of experiments that were done with spin 1/2 particles. Okay, so using this setup of calcium atoms and polarizers, Clauser was able to show that a Bell's inequality was in fact violated. So this was, a major blow to the idea that a hidden variable theory could somehow explain the results we see. So it seemed to be leaning towards quantum mechanics is the correct theory. And it was convincing evidence, but there was one small loophole with it, and that loophole was the fact that Clauser's polarizers were preset along their chosen axes before um, before the photons were launched going towards them. Okay. Now that may not seem like such a big deal, but if you're a very staunch proponent of a hidden variable theory, you could make the claim that, well, if the detectors were already preset along their axes, then maybe it's possible that A's measuring device and whatever setting A was at could somehow influence B's measuring device, right? Kind of similar to how we talked about depending on whether or not A was measuring along SX or SZ, that could affect what was happening over here at B's measuring device. So same sort of thinking kind of close to those lines. It's not immediately obvious a priori how A's detector would affect B's detector, but there's always, there's still a little bit of wiggle room there. You could always say, well, such and such could still happen, even though Clauser's experiment was still pretty good. And so in order to rule out this idea of one of the detectors possibly influencing the other because they were already set along a certain axis before the photons were headed towards them. So one way around that was Aspect's experiment, which he did in 1982. And basically what his experiment did was it eliminated this possibility that somehow you could have influence between the detectors. Okay. So Aspect's experiment was also very well known. In fact, it won him the Nobel Prize in 2022 last year. And so, again, similar to Clauser's, he used a pair of photons that were entangled, and he had polarizers, right? But the difference between the two experiments is that Aspect added a switch that would allow him to change the direction of the polarizers after the photons were already emitted. So, and even more importantly, the switch was able to change the polarization direction quick enough such that information about what Alice measures wouldn't have enough time to reach Bob without traveling faster than the speed of light. So by doing this and making the switch for the polarizers that quick, it rules out the possibility that A could somehow influence what's happening at B, because as far as we know, information can only travel as fast as the speed of light. It can't go quicker than that. So if you're switching this quick enough, there shouldn't be any possible way the information over here at A can somehow reach what's happening over here at B. Okay. So Aspect did this experiment. It was also even more precise than Clauser's experiment. So the results were more convincing, and we didn't have this issue of detector A influencing detector B. So he won the Nobel Prize for that in 2022, and it seemed to be very convincing evidence that a hidden variable theory wasn't the correct description of what we saw in nature. So Clauser and Aspect and these other experimentalists were able to show us pretty convincingly that quantum mechanics seems to be the best theory we have at the moment. So despite quantum mechanics, as Einstein has famously said, it's very unintuitive, it's strange, it doesn't seem to coincide with the reality that we're all used to or that we perceive. Despite all of the weirdness about it, it still seems that it's the best theory we have at describing nature, at least at the microscopic level.